A correctly interpreted seismic section can be used to balance cross section. This becomes a separate study how to interpret seismic images. Here is a snapshot. This is the seismic image from the coastal area from the Indian east coast, and we know that this terrain has been under an extensional tectonic regime. Indian east coast was long back joined with Antarctica and extension happened. Therefore, our tendency from the uninterpreted image to the interpreted image is to fit normal faults. Normal faults are produced in extensional tectonic regime, and here is the interpreted image. Going into the detail, the interpreter has identified the early post-rift sediments, syn-rift sediments and the pull-apart basin, and has also demarcated the basement cover contact. If the seismic image interpretation goes wrong, if one thinks that on the Indian east coast an extensional tectonic regime tries to fit reverse faults, then the starting point of cross section balancing goes wrong. Therefore, the balanced cross section will certainly be wrong. So, as much as possible, accurate interpretation of the seismic image becomes important. Consider a case of folds associated with reverse faults, and consider that the folded rock has been studied in 3 transverse sections. This can be profile A, this can be profile B. This one is, by the way, schematic diagram, and here is the profile C. Now, one can try for cross section balancing, and instead of relying on one particular section, relying several sections can give a better idea. If the cross section balancing is done properly, then it can give us useful information about the suitable drilling sites for hydrocarbon exploration. Let us take a case where the line length balancing can be performed. Consider flat, ramp, and then again a flat, and this is the thick layer before deformation, and within this layer, actually inside it the flat has developed. Then the ramp cuts the layers, and then again flat runs parallel to the layers. Now, suppose here a push is made and the present day situation has come. With this knowledge in mind, and now that this section is given, we might be able to go back during cross section balancing, leading to a proper restoration. In this particular case, constant length and thickness were assumed during the restoration. Both of them have been applied, which means that this line length AB is same as sum of these 5 lengths A, B, C, D, E and F. The length AB plus BC plus CD plus DE plus EF is equal to the AB length undeformed. The same thing has been done for the other layers also. These are the other layers. By doing that, one is able to reach the restored section. So, this is a successful case where the line length and the thickness have been assumed constant. Let us take a set of reverse faults which are listric and mutually parallel, and this particular layer is in focus. This is a portion where we are finding the undeformed rock. Since this part is undeformed, we go by this thickness T0. Although we are looking at the final product, T0 is the initial thickness, because it is undeformed portion. So, this thickness must be same as that of the undeformed rock altogether. Now, a partial restoration is done here. In this process, the length is L1, the thickness is T1. Note that T1 is different from T0. In the process of restoration, since T1 has come different from T0, one can find out how much is the total area in this case. The area is L1 multiplied by T1. Now, to maintain the T0 same as the initial condition, this T1 is altered to T0. So, T0, and then how much should be the L0? L0 should be such that T0 multiplied by L0 should be equal to L1 multiplied by T1, this area. Once that is done, we are able to find out the L0 length. Now, based on the drawing of T0, the L0 length is also drawn. So, from this stage to this stage, an area balance is performed, and this satisfied the initial length T0 same as that in the undeformed portion of the rock, making things more logical. One novel application of cross-section balancing is to find out the depth of detachment and the deep direction of detachment. Consider this as a final product that you have obtained from field work, and here is the initial condition, which is the cross section after being balanced. What has happened here? We are finding a folded layer, and through some studies we have come to know that at some depth lies the detachment. This is the detachment over which the rock has been folded and below which the rock has not been folded. So, here the rock might be very hard, whereas this rock might be soft, prone to deformation. We are dealing with a compressive tectonic regime whereby a fold is produced. The question is, can we find out this depth of detachment? That is the first statement. To do this, we can set the pin lines where we have set where the layer is not folded, as we see it is horizontal. We could have also set here or there, the result would not have changed. Second observation, the pin line is perpendicular to the undeformed layer of the bedding plane, so also here. Now, this area can be obtained. I have already discussed with you in such situation how to find out the area. Divide this line into equidistant points, drop normals and apply the formula. Once this area is obtained, let us say this area is A0, from where this area gain has happened, we consider that this pin line, or we now call it a loose line, because now we are going to move it and call this for certainty as the pin line. Now, this loose line might be somewhere here, and in the process of this shift, the area loss must be equal to the area gain. We can apply the formula area loss equal to the area gain. Then this rectangle's area should be equal to A0, as A0 is the area obtained here using this process. This A0 must be equal to the depth of detachment D, which is here, depth multiplied by the distance between the loose lines before and after deformation, that is the distance between the loose lines. Next, we will apply the line length balance method, whereby we find out this curved line length between one pin line and one loose line. Then we will straighten this line. In other words, say this is the L0 length, just open it up and make it straight line. The moment you do, you obtain the DL length. DL is this much length. I will also demonstrate it using actual practical exercise. Once the DL is known and that A0 is known, D is obtained as A0 divided by DL. In this way, the depth of detachment can be known. It has been known as per this diagram, and there might be a scale involved, that 1 centimeter in sketch or in cross section is equivalent to x meter in reality or in field or in prototype. Therefore, this d centimeter measured will be equal to xd meter, and this is the actual answer, the depth of the detachment. In the next phase, we will see how to find out the deep direction of detachment. Suppose there are two folded layers, one over here and another over there. We find out the depth of detachment from this portion and the depth of detachment from these portions. For this portion, we find out, say this is the depth of detachment, and for that portion of the folded layer, we find out that as the depth of detachment. If this point B has gone deeper, then we say that the deep direction must be from A towards B. If A and B are at the same depth, we say that the detachment is horizontal, and in case point A is deeper and B is At a shallower depth, we say that this is the deep direction. When we prepare the cross section, we know the geographic direction, say this is northeast just as an example, and that is southwest. So, in this case the answer will be deep direction is towards southwest, whereas in this particular case we say that the deep direction is towards northeast. When the detachment is horizontal, then it has no deep direction, because a horizontal plane is not dipping towards any direction.